This is Dr. Brown. I'm just making a very short video sort of reinforcing what I talked to you about in an email about not using the rational zero theorem when you are looking for the real zeros of a polynomial function. Just to give you an idea what the rational zero theorem was, it's basically a guessing game, and you basically take the last term of the polynomial and look at all its factors, which would be plus or minus 1, plus or minus 3, plus or minus 7, and plus or minus 21. And then you look at the first term in the polynomial, which is x to the fourth, and its coefficient is 1. So its factors could be plus or minus 1. And so you look at all at P over Q, all the possible combinations, and you would say P over Q combinations are like 1 divided by 1, plus or minus 1, 3 divided by 1, plus or minus 3, plus or minus 7 divided by 1, and then plus or minus 21. And so these are the possible real zeros. Obviously there could only be 4 because the degree of the polynomial is 4. But what you would do now is test all of these by using synthetic division. Now folks, that is a pain in the neck. Nobody uses that anymore to find the real zeros of a polynomial. They simply use their calculators, and it takes a lot less time. So go ahead and put this function in your calculator, and then if you go the standard window, it looks like this, and you're sort of seeing the zeros here, minus 7 and minus 3. You can also expand x min and x max and make sure there's nothing else out there. But then if you change your y min and y max so that you can see what the function is doing, you have to change it to minus 200 to plus 200. But obviously now you'll see that a real zero is minus 7 and also minus 3. So the answer to this, very simply, is minus 7 and minus 3. And you're through with that. There are only 2 real zeros in this fourth order polynomial. That also means that there are more complex conjugate zeros, and they can be calculated by using long division. Now, in this particular problem, in homework 5.5, I believe it was number 13, they didn't ask you to do that, but I can briefly show you, using long division, how you could get to the complex conjugate zeros. Basically, you know, since the zeros are minus 3 and minus 3, then minus 7 and minus 3, that the factor's got to be x plus 7 times x plus 3 times some, we'll call it polynomial of x, that now equals the overall polynomial. So multiplying x plus 7 times x plus 3, we get x squared plus 10x plus 21. So now we can divide x squared plus 10x plus 21 into the overall polynomial, which is x to the fourth, plus 9x cubed plus 12x squared minus 11x plus 21. And let's go ahead and do a long division. X squared into x to the fourth goes x squared times. Multiply x squared times all of these terms, and you get x to the fourth plus 10x cubed. Plus 21 x squared. And now subtract, just like you do in long division, you get 0. 9x cubed minus 10x cubed is minus x cubed. 12x squared minus 21x squared is minus 9x squared. And bring down your minus 11x and divide x squared into minus x cubed, and you get minus x. Now multiply the minus x times all of these terms, and you get minus x cubed minus 10x squared. Minus x times 21 is minus 21x. And now subtract, you get 0. And then minus 9x squared minus 10x squared happens to be just 1x squared. Minus 11x minus 21x happens to be 10x. And bring down your 21. And if we got the right zeros to start off with, this should come out with no remainder. And we'll see that it does. X squared goes into x squared one time. Multiply, we get x squared plus 10x plus 21. And subtract, and we get 0 remainder. And so the remaining factor is x squared minus x plus 1. So you can see that it has no real zeros, because if you use a quadratic formula, set that equal to 0, a is 1, b is minus 1, and c is equal to 1. So solution is x is equal to minus b, which is 1, plus or minus the square root of b squared, which is 1, minus 4 times a times c, which is minus 4, divided by 2a. A is 1. So 2a is 2. So notice this is going to be x equal 1 plus the square root of minus 3 divided by 2. And that's going to be 1/2 plus or minus the square root of 3 over 2i. So this is the other complex conjugate 0. And I think some of the ones in the homework that are complex are a little bit easier than this. But anyway, this is what you would do if you had to find all of the zeros. The main thing I wanted you to realize that I don't want you to worry about using the rational zeros theorem.